Okay, here we are at lecture number 3. We're going to talk more about experimentation, not being superstitious, and then move on and jump into biology towards the end of the lecture. All right, I told you about what a hypothesis is. Observation, hypothesis, experiment, analysis, result, and then revision and try over again. This is a good way to approach virtually every question in life. What's the difference between a hypothesis and a theory? The difference is really nothing more than that the theory is a well-proven, irrefutable hypothesis. Remember, there's always more data. Things can change. But typically a theory is a very solid piece of information. A hypothesis becomes a theory when there's enough agreement that, like, we can't find any alternative explanation. This has to be the case. All right, so how do you do an experiment so that you can arrive at a hypothesis and eventually a theory, then perhaps a law? There's several key components. One component is the treatment. The second component is the experimental group, which I talked about when we talked about echinacea. The third component is the control group, as important as the experimental group. Why? Because if you don't have a control, you don't know what would happen if you hadn't controlled for variables. I'll explain more about that in a minute. And then finally, there are the variables. These are things that either you change or that change as a function of the experiment. Two different types of variables. So we can control some of those variables. We can control the temperature in the room. We can control how loud the sound is or what drug we're giving a person. And there are some variables we can't control. Changes in gravitational flux that are out of our control. So we try to take into account as many variables as possible, control those that we can, and then monitor those that we cannot. Independent variables are variables that are independent of the experimental process. That is, things we control at the outset. Dependent variables are those variables that result from the process. All right? So you eat a bunch of food, you can control the food intake. How much do you weigh at the end of the experiment? That's the dependent variable. It's dependent upon the experimental process. All right, here's an example of a bad experiment and then a good experiment. And this is also a good example of how you should not be suckered in by a bad experiment. Here they put a balloon in people's stomach to solve a gastric problem. They filled the balloon with a refrigerant and claimed that of all the people they tested, which was a small number, 100% were cured. When this experiment was done correctly, controlling for variables, splitting the group into control groups and experimental groups, and using a refrigerated liquid versus a non-refrigerated liquid, it turned out the results were identical in both cases, and only a small percentage, a relatively small percentage of the people realized any benefit from the experiment. Like with echinacea, there may be a subset of people who realize a benefit, but the majority of people do not. So I recommend you don't have a balloon full of refrigerant stuck into your stomach. I mentioned this before, an effect, a very powerful and important effect called the placebo effect. Our minds are powerful controllers of our body. If you convince your mind that your body has a certain characteristic, there is an increased likelihood that characteristic will become manifest. All right? So it doesn't mean that if I say grow muscles, my muscles are going to spontaneously grow. But there could be a component of mindfulness in any experimental output. Therefore, the placebo effect is taken into account when designing and analyzing an experiment. Controlling for bias is very important. For example, a blind experiment is one in which the subject doesn't know whether they're getting the treatment or the placebo. A double-blind experiment is one in which both the experimenter and the subject do not know who is getting what treatment. They only know after they've analyzed the results, and that eliminates any inherent bias. All right, so a good experiment is blind or double-blind, it's randomized, and the results are analyzed irrespective of the input knowledge. Enough about experimentation. Now here's some reality. The world is rife, is replete with, how do I say this nicely, baloney, misguided non-truths. All right? The agenda behind that could be ego, it could be money, it could be anything. But the bottom line is, as the public, we are often misled by manipulated information. For example, this was an experiment that showed that a certain treatment could cure HIV. After the experiment was done correctly, it was shown definitively that is not the case. We live in a world currently with COVID where there are a lot of alleged treatments, and one must be very careful in selecting those treatments, if any, that actually have some beneficial result. Here is a very important experiment showing that even if you don't think you have internal bias, you probably do. In this experiment, the reviewers were either allowed or not allowed to know the gender of the author. When they knew the gender of the author, female authors were less likely to be published. Now, this is an older experiment. This data is extremely well known, and lots of mechanisms have been put in place to try to rectify this internal gender bias. As we all know, all kinds of bias still exist, and it's incumbent upon each individual to ferret out those internal biases, and it's not always easy and obvious. That's why experiments like this are so important. So bias can influence the interpretation of results, and you must take into account that bias in achieving the most accurate analysis at the end of any experiment. So once we have experimental data, how do we view that data? Sometimes it's very simple, it's on or off. Many times the data are complex, and so graphical displays of data end up being very, very powerful to quickly give the gestalt, the overall impression of this experiment without diving into the minutiae. Now, sometimes that can get so incredibly complicated that really the gestalt is all you're going to get. Like in this picture here, which simply shows a color coding of a massive amount of data. And just by looking at the colors, one can determine the relative output of this experimental process. The point is, graphical output is really important. In analyzing data, it is important to apply robust statistical methods. Okay, statistics are mathematical tools for looking at the meaningfulness or lack thereof of correlations between data. Brian Fantana says, 60% of the time, it works every time. Bad statistics. I'll explain more in a minute. Okay, statistics are a set of mathematical tools to help one analyze the meaningfulness of correlations. Positive correlation is when one variable correlates with the occurrence of another variable, but it's always important to remember correlation is not causation. Critical attention must be paid to both the statistics and the experimental design to determine if there is a causative correlation between two phenomena. As I mentioned earlier, we are subjected to a barrage of what's called pseudoscience and anecdotal evidence. Pseudoscience is disseminated under the guise of science, but the underpinnings are not there. Good experimental design and good statistical analysis have not been carried out. Anecdotal evidence are observations that are observed by individuals or a few times here and there, but they're in no way correlated or validated in any meaningful experimental process. One example is shown here. I can say 4 out of 5 dentists surveyed recommend sugarless gum for their patients to chew gum. How many dentists do we need to survey to make this statement? Only 5. 4 out of 5. We didn't say 495 out of 500, which would be a much more statistically robust number. We said 4 out of 5, and the statement sounds very cool, but it doesn't mean much at all because the numbers are so small. Anecdotal observations about autism and vaccination led to a huge upheaval with respect to people being willing or not willing to vaccinate their children. Now, vaccines contain components. Those components have impact on your physiology. The vast number of vaccines are far more beneficial than any chance of harm. But this made the front of Time magazine because this anecdotal evidence was so psychologically profound. Here's a very smart man, Carl Sagan, now deceased. Read this quote. I won't read it to you, but basically science is a way to overcome the agendas of people who spout anecdotal and pseudoscientific diatribe. So pseudoscience and anecdotal evidence can lead people, naive people, gullible people, to believe things that are not true, and oftentimes are driven by very personalized agendas or fear or some other phenomenon that is not, in any way scientific. Now, there are limits to what science can do. I've been touting the power of the scientific method, but your belief system, your irrational components of however you want to construct your world, is not related to scientific endeavor. All right, I can't do a scientific experiment to test a belief system for which no experiment can be done. All right, that's the end of this lecture. We're going to talk about the keystones of biology throughout this course: life, genes, diversity, and ecology, and ultimately evolution, which ties everything together on planet Earth. Have a great day.